شاء الله النهارده هكلم عن smart assistive device for multiple sclerosis patient with deep sensory loss. المشاكل اللي بتقابل البيشنت معانا بيكون احنا due to multiple sclerosis we know that multiple sclerosis disease is an autoimmune disease causing demyelination. This will cause deep sensory ascending will affect deep sensory ascending pathway. Demyelination in deep sensory ascending pathway interfere with the sensory feedback to the brain. Therefore, the normal pathway, the posterior column medial lemniscus pathway, that is responsible for carry the sensory modalities for the brain, such as fine touch, vibration, and proprioception. The spinocerebellar tract also is responsible for unconscious proprioceptive information for the brain. Due to demyelination, the plantar surface sensation of the patient will be affected due to demyelination of the axon, as we said. Therefore, we need a solution for the multiple sclerosis patient to help them to keep their balance and their posture stability. In addition to the pharmacological treatment, we need also assistive orthotic devices that may help in patient quality of life, to improve patient quality of life. The problem is the damage due to demyelination slow down or blocks down messages between plantar surface and brain. Loss of plantar surface sensation affect normal gait and balance, posture control, and result in imbalance and gait dysfunction, and patient may fall. The solution proposed here is smart assistive to bypass damaged nerve and transmit plantar pressure information through alternative pathway to the brain to improve balance and gait. Due to neuroplasticity and rehabilitation, patient will be able to use their back muscle instead of foot sole. The smart assistive device consists mainly of two parts. The first part is a pair of smart insoles to be inserted in the patient's shoe. And the second part is the vibratactile belt that stimulates the patient back instead of the foot. Here, the main component of the device consists of 6 sensors per foot. Each sensor will go through microcontroller to be transmitted through wireless module to another wireless receiver to receive the message and initiate the microvibrator in the patient back in the belt. The smart assistive device operation during gait, how it works. The first here in the first contact phase, the heel only is in contact with the ground. Therefore, the sensor corresponding to the heel is on. Therefore, in a mirror, exactly we transfer this signal to the patient back in a specific location by initiating microvibrator. In the mid-sense phase, all the sensor will be intact in the ground. Therefore, the all sensors is on, and consequently, the all microvibrator in the right side of the patient will be initiated. The insole, the actual shape of the device, here is the first picture shows the smart insole contains 6 flex sensor sensing resistors that take the stimuli and then transmit it to the patient back. The second part is the vibroprotective belt around patient waist, containing the 6 small micro vibrating motors that initiate the patient back. To know the efficiency of the device, we validate the device through 2 experiments, one for standing posture balance and one for gait. 4 patients with multiple sclerosis were selected due to inclusion-exclusion criteria. All the patients were EDSS between 4.5 and 5.5, and with fair motor power. Each of participants is asked to stand quite as possible. And during quiet standing, the patient will be in 3 different postures. The first one with eyes open and feet shoulder width apart. The second posture is with eyes open with narrow base of support, and the third posture will be with eyes closed and feet shoulder width apart. Each posture of the 3 postures will be repeated twice, once before using the smart assistive device and then again with the smart assistive device. Here the results showed that there was a significant difference between without the device and after using the device. The left column showed a healthy control graph for kinematic measurements taken through a capture motion system. We measured the trunk pitch angle range of motion, trunk tilt angle range of motion, and also we study the trunk angular velocity and trunk angular acceleration. As we see in the graphs, the left side show the healthy control. The middle column show the patient with multiple sclerosis without using the assistive device, and the right hand side show after using the smart assistive device results. Here, pitch angle range of motion, tilt angle, which range of motion without device, during the 3 postures, all the patient show greater values than the healthy control, which indicate posture sway. Also, the tilt angle shows the same. After that, the angular velocity, root mean square values recorded for the patient without device were also greater than healthy control, the same for angular acceleration, root mean square values. The device effectiveness for patient with multiple sclerosis, pitch angle range of motion here, we observed that the pitch angle range of motion decreased through trials and in the 3 postures. The blue color before using smart assistive device, and the red color show while standing using smart assistive device. The pitch angle range of motion decreased in 11 out of 12 trials. Here, the tilt angle range of motion decreased in 9 out of 12 trials in the 3 postures. And 1 trial show no change in the before and after was the same. The angular velocity range of motion decreased in 11 out of 12 trials in the 3 postures, as we see in the graphs. The angular acceleration root mean square values decreased in 10 out of 12 trials. Results of gait. The gait assessment for patient with multiple sclerosis is done twice. One, without using the smart assistive device, and again after 1 week training of using smart assistive device. And as we see in balance graphs, the same here in gait assessment. The left side show healthy control. The middle column show the patient with multiple sclerosis without using the device, and the right show the enhancement while using the device for 1 week. Pelvis pitch roll angles also was greater than healthy control, as we see in the middle column. We have the values greater than the healthy control on the left hand side. After using the smart assistive device for 1 week, patient with multiple sclerosis shows enhancement in pelvis pitch roll angle. Here, the values of device effectiveness during gait. Trunk pitch angle decreased about 84%. Trunk tilt angle range of motion decreased by 89%. Trunk angular velocity about 57%. And the last one is the trunk angular acceleration decreased 53%. After testing the device, we asked each participant to answer a questionnaire to know the perspective of the patient about the medical device. All participants said that it was easy to use. They feel the vibration well. They could differentiate between the right stimuli and the left stimuli. They felt better in balance. They felt safe while using the device. They didn't experience any skin irritation. However, all participants said that the appearance of the device was not good so far. They were impressed to be seen by other people while wearing it. They commented also on the belt size and on the battery weight. Conclusion: as an initial prototype for proof of concept, we designed a smart assistive device that will be used by multiple sclerosis patients with impaired gait and balance due to deep sensory loss. The device showed improvement in balance and gait, and the study limitation were that the study is performed only on 5 patients. The insufficient sample size was one of the limitations. A short period of training, the single testing, and the device appearance also. The main complaint of all the patients was that the battery weight were too heavy. So the future work should include more patients with multiple sclerosis to investigate more, to investigate the device more sample size, and the training period should be longer duration. And about the prototype, should be after that may be slim in size, slim, or maybe yes, maybe under the patient clothes to avoid embarrassment. The device can be extended to be used in other diseases on the same concept of that causing deep sensory loss, for example, the diabetes. The device may be manufactured in Egypt to be the first local-made device designed here for that purpose. The device can connect to mobile applications to analyze balance and gait characteristics during daily life. That's it. Thank you.